So this one looks really complicated because it's got a couple of functions in it. We've got the cosine function, 5x is a function. We've also got sine squared is a function. Originally you might think, oh, well, she told me anytime there's not something besides anytime there is something besides the x inside the cosine or sine function, I should just do that as my U-substitution. But that wouldn't really get us anywhere. We would end up with cosine u over sine squared u, and we don't know how to integrate that. So let's try a different U-substitution. I do see a function and its derivative, but I see two different functions. Like I see cosine and its derivative sine, and then I see sine and its derivative cosine. So how do I know which one to pick? Well, I'll tell you, at first I didn't know which one to pick. At first I was like looking at it and I'm like, oh, do I pick sine or cosine? And if you pick cosine, you would end up with 1 over sine cubed because remember when we do U-substitution, a lot of times the derivative ends up in the denominator. So that's a problem. So that's when I thought, you know what? Let's do the other route and let's do sine. We're going to substitute in sine, and then we can get cosine of 5x eliminated. So let's try that. So we have a U-substitution of I said sine, and then I almost tried to do it cosine. Sine of 5x, just sine of 5x, okay? Because remember, this is the same as sine of 5x squared. It's the same thing, so we're just going to put a u in there. Okay, so du equals, well, the derivative of sine is cosine 5x, and then we have to multiply by the inside function, which is the derivative of the inside function, which is 5. And then we have dx. So we have dx equals 1 over 5 cosine of 5x. And this is going to help us du. This is going to help us a whole lot because now we have a cosine on top and a cosine on bottom. We can cancel them out, right? Okay, so let's come back over here and let's do our U-substitution. So we have cosine 5x on top. We have u squared on bottom because u was sine 5x. We have 1 over 5 cosine of 5x. And then du. So there's cosine 5x, there's cosine 5x. And we're left with 1/5, which we can bring outside the integral, 1/5, 1 over u squared du. And your first thought is going to be like, oh, that's ln, right? No. Remember, this is like, we can just rewrite this as u to the negative 2. Okay, so just because 1 is over something doesn't mean that we're going to use ln, because we use ln when we have 1 over something with a power of 1, because we can't subtract 1 from that because then we get something to the 0, so that doesn't work. So we're just going to rewrite this as u to the negative 2, and then we just integrate it, right? Okay, so this is 1/5. Well, we add 1, so that becomes negative 1, and then we divide by that power, which is negative 1 plus c. Okay, so that ends up negative 1/5 u to the negative 1 plus c. And now we just have to plug u back in. What was u? Well, u was sine 5x. So we have that equals negative 1/5 sine 5x to the negative 1 plus c. And we could just leave it like that. You could put the sine 5x on the bottom of the denominator if you really wanted to, but you don't have to. Oh, the other thing you could recognize is that 1 over sine x, that's what else I was going to tell you. This is 1 over sine of 5x. What is 1 over sine? Well, that's cosecant. So we could write this as negative 1/5 cosecant 5x plus c. So either one of those works. They're all three of these. This, all totally fine. Okay. Here's this one, and we recognize it's got to be a U-substitution because I see a function and its derivative right there. Okay, so u is going to be tangent theta, and so du is secant squared theta d theta, and so then d theta equals du over secant squared, which is perfect because we need secant squareds to cancel out. So now we can go ahead and do our U-substitution. So we have secant squared theta over u du secant squared theta. Those cancel out, and we end up with 1 over u du. Well, what's the integral of 1 over u? That equals ln of absolute value of u plus c. And what was u? Well, u was tangent theta, so that equals ln of absolute value of tangent theta plus c. And that's it. Okay. We're going to integrate tangent squared. Oh no, we don't know how to do tangent squared. Okay, so here's the thing. In like Calc 2, we get into tons and tons and tons of like trig identities. They're actually kind of fun, challenging but fun. So we have to, a lot of times when we have trig things, like we would integrate things like sine to the fourth, things like that, that we just don't have like a ready-made answer for. So how do we integrate tangent squared? Well, this wouldn't work to do a U-substitution because the first thing you're going to think is, oh, I'll just do a U-substitution for tangent x, but then we end up with secant squared x in our U-substitution because, you know, du and all that jazz. So we have to use trig identity to replace this with something else. So remember, the most important, most common trig identity, and the one we're using in Calc 1 is sine squared x plus cosine squared x equals 1. So when we want to figure out what tangent squared equals, remember we just take all of these, and we divide them by cosine squared x. Just pretend like I can write small really well. Those are terrible. Okay, so then what do I end up with? I end up tan squared plus 1 equals secant squared. Okay, so we can now replace tangent squared with secant squared minus 1, right? Because that's what this equals. If I just subtract 1 from both sides, I get that tan squared x equals secant squared x minus 1. And I know an integral that has secant squared x in it, right? So I can use that. Okay, so this is the integral of secant squared x minus 1 dx. Now let's integrate that. We are going to have the integral of secant squared is tangent, so this is tangent x, and then the integral of 1 is x plus c. That's it. That was so easy, right? Okay. Last but not least, find the area bounded by these two curves, 2 cosine, and so on. Okay, so let's first do this in our calculator. We're going to bring up our calculator here, and we're going to put these in our calculator. Make my calculator as big as possible. Okay, so we're going to go to y equals, and we're going to let me make sure this is on. 2 cosine x, and then we're going to graph 1/2 cosine, just kidding, delete, that would be tangent of x. We're going to graph them. Okay, and then we're going from, and x equals 0, so we're going to take this little, let's see if I can do a zoom box here. We're going to do a little zoom box because we're looking at the area of the curve bound by and x equals 0. So we're going to do our little box zoom here. So we're looking at this piece right here, okay? So I'm going to go ahead and sketch that really quick on mine so that I've got it. And then kind of, let's see, like, let's do a different color. All right, so the other thing that we need to calculate is we need to figure out where they cross. So let's do second calc, and we're going to calculate their intersection. And they intersect when x equals 1.081752 and y equals 0.9395649. Now, one of the cool things that I didn't know about this is this automatically stores your x and y's in your calculator, so you actually have these. So if I go back here and I do alpha x, I actually get that x value that I just calculated, right? And then if I do alpha y, it's going to give me the y value. So those two are already in my calculator. So that's super great. Awesome, awesome, awesome thing to know. Okay, so we're going to figure out the area of this curve. So let's go back here. All right, so first things first, we're going left to right, right? Because our representative rectangle goes this way. And so we're going to go left to right, like if we're, scanning, because our top curve would be the red one and the bottom curve would be the right one. So we're going to have the integral from a to b, like from left to right. So the left integral is 0, right? That's the left bound of this one. And then the right bound of this one is going to be this x value right here. It's going to be this point right here, which is 1.08 and blah, 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 blah. And it actually, you know what? We know that that's stored in our calculator as x, so let's just put x there. And then we're going to do the top curve minus the bottom curve, so that's 2 cosine x minus 1/2 tangent x dx. So we just set that up. And now we go back to our calculator. And we're going to figure out what this integral is. So we're going to go to math. We're going to find f(int), and we're going to go from 0. And remember, our x is already stored, so we're just going to use x right there. And then we're going to take our top curve, which is y1. So we're going to go to vars, y-vars, function y1 minus vars, y-vars, function y2, and then we're integrating with respect to x. We push enter and we get 1.3878. So we can round that, round or truncate. 1.387 is what I would prefer. We just, that is the area in between the two curves.